Welcome back to ECE 442-542. What we want to talk about in this presentation is an overview of compensator or controller design, and we'll do that by first looking at this comparison between an open loop system and a closed loop system. We'll talk a little bit about the benefits of feedback, and then we will end this overview discussion of controller design by talking about internal stability, which internal stability really, when I say that phrase, I want you to be thinking, oh, my controller cannot cancel poles and zeros in a discrete time setting that are outside the unit circle. That's what I want you to think when I start mentioning or comment on internal stability. Let's now talk about controller design, or I may refer to that as a compensator design, and it's all going to be centered around this understanding of a block diagram where we have our system that has an input U and an output Y. And why might we want to introduce a controller? Our system itself might be naturally unstable. One common example of an unstable system is an inverted pendulum, or can you balance a yardstick in the palm of your hand? Or you could think of it as a Segway. A bicycle, you could think of balancing that on the two wheels as like a inverted pendulum. A unicycle, I guess, would be something similar. Or even a rocket, that you can view as an inverted pendulum, and you're now trying to keep that stable so that you can direct that rocket to the location that you want it to be traveling. Another reason we might want to introduce a controller is because in our systems that we create, a lot of times there's uncertainty in those systems, and that uncertainty might be due to manufacturing tolerances, for example, uncertain masses, uncertain springs, inconsistency in our dashpots, which are removing energy from the system, unknown or not unknown, but maybe tolerances on resistors and transistors might be quite large, and those now present manufacturing tolerances that we want to design a system that in the face of those uncertainties, we still have a system that performs accurately and consistently the way that we want it to behave. We could also have uncertain parameters due to aging of the system, or the parameters now change as the system gets older. Where our desire now is we want a stable system that has acceptable transient and steady state behavior. And you'll see that as we move through the remainder of this course, those two behaviors, transient behavior and steady state behavior, will be competing, or we may have to balance those two or trade those two behaviors off against each other. We might have a transient behavior specification, and we might have a steady state accuracy specification. It may be that we have to loosen one of those constraints up, or those desired targets up, in order to achieve the other. And this desired system that we want to achieve, we will now call capital T sub C, and that's this desired system behavior between a reference input R and an output Y. Now, with respect to a controller, we could really accomplish a control either in an open loop setting, where we now simply stage a controller with a transfer function capital C of Z in series with a plant G of Z, so that we now have these in cascade or in series, and the overall transfer function would be capital T sub C of Z. Or we might put this controller plant combination into a feedback configuration where we are measuring the output Y from our plant, feeding that back and comparing that with a reference signal. That produces an error. That error now is injected into our controller. The controller now drives our system U of Z, our control, U of Z, drives our plant, G of Z, in this closed loop configuration, and the transfer function between the reference input R and the output Y is capital T sub C of Z. What we want to do now is compare these two structures, the open loop structure with the closed loop structure, and try to illustrate why we probably are leaning towards a closed loop structure in this particular class. First, let's look at the open loop structure, where again, capital T sub C of Z is our desired controlled transfer function. And some difficulties that we might see relative to this open loop structure is it actually lacks robustness. And what do we mean by robustness? By robustness, we mean if some parameters change in our system, will our system still behave the way that we would like it to behave? And if it does not, if parameter changes or changes in the parameters dramatically impact the behavior of our system, then we will say, oh, that system is not very robust. So if we have parameters in our system, G of Z, that are unknown or change, then we may have poles and zeros and uncertainty in our gain. Let's just look at one particular fairly simple example. Suppose that our system, G of Z, is not much of a system. Suppose it's simply a constant, and let's call that constant capital G, or I'm sorry, lowercase g, just to remind us that that's our system G. Now our desired closed loop transfer function we could write as capital T sub C of Z is the product or the cascade combination of our controller, capital C of Z, with G of Z. If we want good tracking, that is, if we want the output Y to look like the R, again in our open loop configuration, here if we put in an input R, we want the output Y to look like R, then for this open loop system, one way to make that happen would be to just make capital T sub C of Z be 1. And making it 1 is possible if we allow our controller, capital C of Z, to just be the inverse or the reciprocal of the plant itself. And in this particular example, we're just saying, assume a very trivial plant where that plant is just a constant G. So now we are able to accomplish this desired transfer function of 1 if we make our controller the inverse of our plant. But what happens if our plant is not really G, but it's something else? It's G bar. It's a different constant. Then what happens? Well, now we have a modified a modified transfer function between the input R and the output Y. It's still C times G, but remember, C was based on, our controller was based on a nominal plant of G, so it's now 1 over G. But let's say that our true plant is G bar. Now, G bar divided by G, since G bar is not equal to G, is not going to give us 1. And that now says that if we looked at the location where we want to go, which is R, that's the blue line, and where we actually end up, now we're assuming that G bar is less than G, just in this illustration for illustration purposes, then we are going to have a gap or an error between where we wanted to go R and where we actually ended up. And that was just because we were assuming an open loop configuration for our controller plant combination, and there was actually some uncertainty in our plant. Where if we look at just writing through the equations, we see that the error is this difference between R and Y, R minus Y, R minus, and now Y is just G bar over G times R, and we can see that this error is now going to be influenced by the difference between 1 and G bar over G, or how much change is there between G and G bar, and that may be large and it may be unpredictable. And if we're operating in this open loop scenario, that may not be acceptable. And in fact, what we are going to show now is that feedback can help us improve upon this accuracy or lack of accuracy from the open loop scenario. Let's now look at the closed loop case. So if we now look at the closed loop structure, we have our plant G, we have our controller C, and we're feeding back the output Y and comparing that to the input R, the reference input. Now what happens in this particular case? We can derive the closed loop transfer function. That's now GC over 1 plus GC. You should be able to do that by now in this semester. And that gives us our desired closed loop transfer function, capital T sub C of Z. And this is now a way of deriving that. Recall that y is g sub cz times e, with e equal to r minus y. A little algebra, plugging in the e, which is this expression, r minus y, into that, and combining terms that are common with the output y and the input r, divide out the expression, or divide through by the expression that's scaling y, and we now obtain our closed loop transfer function, capital T sub C of Z. That's where this particular expression comes from relative to this closed loop structure in a control design scenario. So we now have this desired closed loop transfer function, capital T sub C of Z, available to us, and we want to see what happens if we have something similar to what we had before. In our earlier example, we said, oh, let's just look at the case where our plant is very simple. Let's just say that it's a constant G. Now let's not worry about the controller being the exact inverse of G. Let's just let our controller be K. If we plug in K for our controller and using this capital T sub C of Z form expression right here, then I hope it's clear that we now have G, our plant, times K in the numerator over 1 plus our plant G times our controller K. Now, if we look at that closed loop transfer function, as capital K gets large, then 1 plus GK basically becomes GK. Then we have T sub C of Z approaching GK over GK, which is roughly 1 or approximately 1, and that's what we wanted. We wanted our desired closed loop transfer function to be 1 so that the input R is capable of being tracked by the output Y. If our closed loop transfer function T sub C of Z now looks to be like it's 1, then whatever we inject into the system at R will appear at the output Y. Now, that seems to convince us, oh, great, now we can use output feedback. Well, if that's the case, then why do we need this class if we could always just put in a very large K, a very large gain into the controller in this feedback configuration and be assured that our input would always track, or the output would always track the input. So there's obviously something more to consider or to worry about than just selecting a controller to be some large gain value. Let's look at another example with feedback, and now suppose that we have a dynamical system. Suppose that we have a system that just is represented by a 1 sample period delay. Suppose that the output Y will simply be the input 1 time step before the present time. So Y is now U at n minus 1. We put in an input U wait one period, and the output will equal that input that we put in. And let's assume now that we have our controller C of Z as some value K, like we did before. It seemed to work before. Let's see what happens now. But now our system is not just a gain. It now has some dynamics. It has some memory. It now is remembering or behaving in a fashion that just remembers what was injected one time stamp or one sample period before. So now let's look at what happens if we inject into this closed loop configuration a step input or a little r of n equal to 1. Or we're now assuming that r of n is equal to 0 and y of n is equal to 0 for all negative values of index n. So that's what we're assuming. So we have 0 memory in the system, and now we hit the system with input r of n equal to 1, and we hold that constant at 1 for all time steps beyond n equals 0. Well, if that's the case, then y of 0 is u of minus 1 by definition. And what's u of minus 1? Well, u of minus 1, if we look at our block diagram, that's k times r of minus 1 minus y of minus 1. But r of minus 1 is 0, y of minus 1 is 0. We gain, or we multiply 0 times k, we get 0. So y at 0, if the system was initially unenergized, leads us to y at time 0 being 0, even though we've hit the system at 0 with a magnitude of 1 for the reference input. So we would expect the output y to start moving in a little bit. But remember, there was a one-step delay. Now, if y of 0 is 0, then we can compute u of 0. That's just k times r of 0 minus y of 0, where u of 0 is a scaled version of the output of that summing junction, where the summing junction's output is r of 0 minus y of 0 at time 0. We scale that by k, and now the input at time 0 becomes k. And y at time 1 is just u one time step before, so y of 1 is u of 0, which is now k. Y of 0 was 0, y of 1 is now we've jumped up to k. Whatever k was, k again was the gain for our controller. Well, now that we have y of 1, we can compare that with r of 1 and generate the input at time step 1. U of 1 is now k times r of 1 minus y of 1, or that's k times 1 minus, and y of 1, remember, was k. Or we've now created a input u that's k minus k squared. And now what do we do? Well, now we know what y of 2 is. Y of 2 is u of 1. So y of 2 is k minus k squared. Y of 0 was 0. Y of 1 was k. Now we're at k minus k squared. And maybe you can start to see a pattern. Maybe not. Let's go one more step. Now that we have y of 2, we can produce u of 2. With u of 2, that's just k times r of 2 minus y of 2. Remember, r for non-negative arguments is 1, meaning this is now k times 1 minus y of 2, but y of 2 was k minus k squared. We distribute that k through the 1 minus k plus k squared, and u of 2 is now k minus k squared plus k cubed. But u of 2 is just what y of 3 is going to be, and now we know what y of 3 is. And maybe now you can start to see a pattern. We started with y of 0, then we obtained y of 1 was k, then y of 2 was k minus k squared, then y of 3 was k minus k squared plus k cubed, and I think you can see then that if we continued this, y of n would be k minus k squared plus k cubed minus k to the fourth dot dot dot, and whatever n is will be plus or minus k to the n. Well, that maybe doesn't look so good. It might be okay if k was less than 1. If k was less than 1, then we're raising this value of k that's less than 1 to a higher and higher power. That's shrinking, so y of n would be well behaved. The tail would shrink and we would be converging to some value. K having a magnitude of 1, we would just be adding and subtracting 1 each time, and then y of n would just be bouncing back and forth between 1 and minus 1. That might not be such a good idea. And if k is bigger than 1, then y of n is going to grow because we're now raising this number that's larger than 1 to a higher and higher power, and that's just going to make y of n go unbounded. So what can we conclude? Well, what I'm hoping that you see is that we can't just fix everything by putting in a controller with a large gain. Here we had a system with some dynamics, and that system with dynamics actually caused this behavior to be unacceptable if we just arbitrarily selected our controller to be a large gain k. Now, we've seen that feedback for a closed loop control can be very helpful, and so the nice thing is we need to be armed with a little bit more knowledge than just injecting or utilizing a controller that consists of only of some large gain value in any given scenario. So we have to be a little bit wiser in how we design our controller. But what we can see or draw from this discussion so far is that there are some benefits to feedback. One is we can stabilize unstable systems. Remember, we have the Segway or the bicycle. We can stabilize those with controller design. We can change the system behavior. We have this trade-off between changing the transients, which the transients are these performance specifications, settling time, percent overshoot, or peak time, and we can improve the steady state accuracy. Sometimes we can't do all of those together, but we have to now trade those particular behaviors with one another. But that's okay. That still allows us to generate acceptable or more acceptable behaving systems. Here is an illustration of what I'm maybe saying. Suppose the blue dashed line in the time domain represents the response that we would like to achieve. That's our desired response. It might be initially, if we applied a controller, we might have this green response of our system, and there you can see that in the steady state, there's quite a large gap or difference or error signal between where we want the desired response and the actual system response that's this green trajectory. Well, if we design our controller more effectively, we could possibly then produce a better controlled system, which is illustrated in red. Now we have a little bit of an overshoot. We go beyond where we would desire our response to be, but we do start to lock on or nearly eliminate the difference between where we are with the red and where we want to be, which is with the blue. So our goal in this class is to transition from green response trajectories to red response trajectories and achieving this acceptable trade-off between overshoot and speed of response. You can see even that the red curve gets to the blue curve quicker than the green curve would, and also steady state accuracy. One property that we definitely want to maintain when we are designing a controller is we need to make sure that the system itself is internally stable. So we need to make sure that not only are we stabilizing the system, but we're also making sure that the system itself, all signals in the system are in fact stable. That's what I mean by internally stable. Stabilizing the system is achieved by accomplishing this desired closed loop transfer function, capital T sub C of Z, which is GC over 1 plus GC, and that's this ratio of the Z transform of the output to the Z transform of the reference input. But for internal stability, what we actually need is we actually are wanting to have more than just that desired closed loop transfer function stable. We actually want three different transfer functions to be stable in this particular configuration. We want the transfer function between the reference input R and the air signal E, and that's not just a unity. We actually can see that that particular transfer function is 1 over 1 plus CG. So we need that this system transfer function needs to be bounded input, bounded output stable. We want to ensure that the transfer function between a disturbance and our output Y is bounded input, bounded output stable, or what that means is if we put in a bounded input for our disturbance, D, we obtain a bounded output for Y, and that's now that transfer function is governed by G over 1 plus CG. We want that transfer function to be bounded input, bounded output stable. And finally, we want to have this transfer function between the reference input R and the input to our system U. We want this transfer function to be bounded input, bounded output stable, and that's governed by C over 1 plus CG. And we need that transfer function to also produce a bounded input, bounded output stable system. We can make those three transfer functions stable, or we can achieve internal stability if we make sure that when we're designing our controller C of Z, and C of Z appears in these transfer functions, as long as we keep C of Z from canceling unstable poles and zeros in our plant G of Z, then we will be able to maintain internal stability. So we have to make sure and guarantee that C of Z is not canceling in the discrete time setting poles and zeros that lie outside the unit circle. And if you want more background on this internal stability concept, you might refer to the Doyle-Francis Tannenbaum reference that we have for this class, which is chapter 3 of that book, or the Ostrom and Murray reference, and I believe that will be in chapter 11 of that particular reference. So if you want more background on internal stability and these different transfer functions, but you should be able to derive these transfer functions between these various inputs and these selected outputs to demonstrate that those yellow, blue, and purple transfer functions are what they are, and that you do not want to have any cancellations from your controller, or you do not want your controller to be canceling unstable poles and zeros in your original system G of Z. That will ensure that all three of these transfer functions are in fact bounded input, bounded output stable.